Good morning, everybody. I'm Dave Cohen. I'm the Storage Solutions CTO in the data center group at Intel. I report to the GM of the persistent memory business unit within the broader data center group. What I'm going to talk to you about today is a solution that we've been working on with Red Hat for quite some time, and give you a little background of why we're doing it, but just so you get a sense, I work for the guy who's going to sell persistent memory, DIMMs that persist past the power cycle. And so he gave me the mission to go disrupt the storage architecture that's in play today and replace it in two ways. First of all, replace hard drives with 3D NAND NVMe devices, which is kind of crazy, and then replace SSDs with persistent DIMMs. And so I'm going to give you a little insight out of what we're thinking here. But before I do, I want to talk a bit about customer pain points. And this is really an industry perspective. So enterprise segment and emerging cloud. The big cloud players really have this figured out. They also have data centers that have no real estate constraints relative to more older data centers that you might see at, say, Coca-Cola. So part of the problem is companies are pivoting to monetize their data and much more aggressively. They see the big cloud guys doing this. They realize they have valuable data, and they're applying machine learning, deep learning, AI analytics very, very aggressively, especially the top end of the Fortune 500s. When they do that, they actually accelerate their data growth, which was already fairly untenable. And so they're looking at ways to disrupt how they manage the storage capacity to store all that data. When you look at it, though, what everyone has done over the last several years is embrace the model that Google perfected back in the late 90s with direct attached storage for MapReduce, right? And that gave root to Hadoop, and enterprises trailed behind the cloud guys by several years. So by the time the Googles and Amazons of the world had moved on, the enterprises were just starting to take Hadoop into their data centers. So fast forward about 10 years, right? So 10 years in, they're adopting. 10 years later, they're feeling the pain points that the cloud guys did back in the mid-2000s, late 2000s. So what happens is if I'm deploying storage in a fixed ratio with my CPUs, then if my data is outgrowing my CPU requirements, I get a lot of CPU cycles that go unused. And I have a really expensive solution in terms of keeping up with my storage capacity. And that gives rise to the desire to physically disaggregate the storage devices into a second tier. And I'm emphasizing physically disaggregate because if I just do this with, say, HDFS or the Google file system, that's not going to be sufficient, right? Because that's not the only way that I access my data. And so then I'd end up with a bunch of silos. And I want to be able to share this infrastructure. So this gives rise to the disaggregated storage model. And then what that allows us to do is scale storage capacity independent of compute. And I'll talk a little bit about what that's predicated in the next slide. The last thing is that no one wants a big monolithic software distribution from anybody, right? Those days are gone. So when you look at the Hadoop distributions, they really have been kind of put to bed, right? Everyone wants to deploy services, whether it's on-prem in a private cloud or on public cloud. So these are really the three pain points we heard from customers over the last couple of years. So In terms of workload, what we looked at is how would we build this infrastructure? And what we realized is we want to build this infrastructure for data-centric workloads. So what you see across the top are the workload categories that we're targeting. At the bottom, I've kind of shoehorned AEP, which is our code name for our persistent memory products. And then storage would be NVMe devices in this case. Network and CPU, so that's the hardware at the bottom. The virtualization layer is basically Kubernetes in conjunction with CNI with networking and a software-defined storage solution. So the networking is based on BGP, and we route to the host. And we use a 3-stage class, and I'll show you a picture of it in the next slide. And then we do software-defined storage, but really this is a brain-dead, cluster-wide logical volume manager for ephemeral volumes that we carve out of NVMe devices. It's not fancy, but it does scale, and it provides very, very high throughput. So workloads run as services. We can run Spark, TensorFlow, and other data-centric execution environments, and they run on the same cluster as the data services. So the platform itself, you can come and look at this on the e-board later, but the platform itself looks a lot like what I've depicted over here in this cartoon. The physical infrastructure is actually disaggregated storage. The disaggregated storage is in the green and red. Those are storage servers, and red is the JBOS, just a bunch of flash. We balance all of that with a 100 gig NIC to 4 NVMe devices. So each one of those is fully balanced against CPU and memory and can saturate the 100 gig link. And we just scale that horizontally across the cluster. We do not, however, allow NVMe over fabric traffic, the block storage traffic, to traverse past the rack. So we don't try to do anything fancy with block being across racks. All we're doing is an incremental evolutionary step over the way that HDFS or the Google file system worked in the past. But instead of trying to do a higher level, very narrowly focused protocol, we use NVMe over fabric and present block. But effectively, we're just replacing local disks. So then the workloads get deployed by Kubernetes. In a Kubernetes world, in a microservice world, in a cloud-native world, every process gets a disk. So in our model, every process gets a volume. And they just scale horizontally. They provide all the resiliency, all the redundancy. We just provide ephemeral block volumes that are carved out of NVMe devices. We don't do any striping. We don't do any resiliency at all. And so the workload I'm depicting here is one where we use S3 as the back end. We provide very high throughput out of S3. We optimize for caching on the local hosts. And caching is really where all the persistent memory focus is. And so the Spark workloads or TensorFlow workloads get serviced out of local hosts. And there's a very nice chain of events where the storage access to S3 does not overlap with the local accesses to the cache. And that fits very nicely as you scale this up to many workloads running at the same time. Come see me later. I'll be around all day. Thank you.